So we looked at different things that we could do to maybe change the way we model this. And that's what we're going to take up for the rest of today. Okay, so we want, this is out of date. This is already on, yeah, I don't know. This doesn't correspond to the dates on the horizontal axis. So, you know, we're already somewhere maybe twice as far along as we were before. But the point here is that it looks like it's growing exponentially here in kind of most countries. You can see in South Korea, they've had fairly strict measures and really rigorous testing of everybody. I think America has only tested maybe 10,000 people or something like that. Not very many. They test 2,000 people a day. So they've got a pretty good lockdown on this pandemic. Italy, it really took off. China, it's slowed down now. Okay, so but you can see that we're kind of where China was before. That things are really taking off. So what I want to do now is create a kind of a more realistic model. You know, you would kind of expect what China got. So you would expect that initially it would go up, right? But you don't think that's going to go on forever, right? At least you'd hope not. So there should be some point where it starts slowing down, okay? But if we have exponential growth, we never get this kind of green part here. We never slow down. It just keeps on going until it takes over the entire world. So the question is, can we create a better model that kind of captures that slowdown of the disease spread? And that's what I've got here. This is a very classic model in mathematics. It's called the susceptible. So this susceptible, let's put maybe some red or something. The susceptible people, the people that can get the infection, they're in this box. You imagine this is all people that are susceptible. And then you have the infected people, they're counted in this box. And the recovered people are counted in this box. Okay? And we're going to make the assumption that recovered people can't get the infection again, which, according to a recent study as of like yesterday or Monday, it looks like at least a few people have gotten reinfected after they were infected by the coronavirus. So what we're going to say is that people get infected at a certain rate, and people are going to recover at a certain rate. Now this is going to it's going to look a little messy, but then we're going to graph it out and then see how that works. So we imagine that based on the number of infected people, so here, this is the number of infected people, and we're going to use the subscript time, t, like this. So these people, they come into contact with susceptible people at a certain rate. And we're going to say, we're going to look at the fraction of susceptible people in the total population. So if I take the number of infected people, the number of susceptible people, the number of infected people, and the number of recovered people, all at any given time, then that's some fixed number. So we imagine there's no deaths due to the disease. There's no, suddenly people aren't having births and bringing more people into the susceptible category, but it's some fixed number, okay? So we look at the proportion of people in the population that are susceptible. We look at the number of people that are infected, and these are going to come in contact with these susceptible people, okay? You don't infect, if you're infected, you don't infect everyone you meet, but you have some sort of probability of infecting people. You have some sort of interaction rate. You may come into a lot of people, you know, if you're a nurse, for example, or if you're one of the people working at the grocery outlet right now, you come in contact with a lot of people. But the disease isn't always passed on. So you have some rate at which the disease is passed on. But what this gives us is a way of finding out, like we did before, the number of people. I'm gonna change my wording slightly. This gives us a way of finding out the number of people infected at a certain time based on how many were infected in the previous time. So you imagine how many people are infected tomorrow, or how many people are infected today based on how many people were infected yesterday. So you could take the number of susceptible people yesterday and some of them get infected, so they're no longer susceptible, they're infected, okay? What this tells us here, and I understand this will look a little complicated, but I've got a nice chart that we'll play with. I just want to show you where it comes from. The number of infected people today is equal to the number of infected people yesterday, plus these new people that just got infected, okay? Like this. So this is how the number of infected people changes. The number of infected people yesterday, plus all these new people that just got infected. And now we're gonna just do another simple thing. We're gonna imagine that some infected people become recovered at a certain rate. And this is gonna be the number of recovered people on any given day is equal to the number of recovered people the day before plus some recovery rate. So maybe you take, every day 70% of all people get recovered. So you take some proportion of the infected people from the previous day and they no longer have the disease, okay? So that's how people recover. But then we include that in this infected equation by subtracting out all those people that leave the infected class, that are no longer infected, okay? And what we come up with is this expression that tells us how the number of infected people change from day to day. So this is just like our simpler example, but now we're not assuming that everyone gets infected, that we just have a certain proportion of people get infected. It depends on how they interact. And we also assume that some people are recovering, that are getting better from the disease. So what we saw in the exponential growth model was that people were just getting infected and infected and infected. And if that was the case, then in 22 days, everyone on the planet has the disease, okay? And so hopefully that's not happening here. So maybe this is a model that will kind of be more realistic. Questions before we advance? Any questions on that? Was it crystal clear or confusing?
It's quite confusing, but I mean, I think after the next couple of steps might be clearer.
Okay, that's good. All you need to know, so the expression is complicated, but all you need to know is it's similar to what we did before, where just neighbors are getting infected. Here, we don't assume the people are standing in neat rows and columns. They're just going about their business in the Bay Area. They're going to the Tool concert a few weeks ago, or to the Bernie Sanders rally or something like that. And some of them are exchanging the disease. They're coughing on each other and things like that. So now people are less organized in rows and columns, but they're all just kind of intermingling. Okay?
Yeah.
So, why did that? Did I really put on a... It's loading because I have an image there, but that image shouldn't be that. Oh yeah, apparently that image is very difficult for this thing to process. That's no problem, I've got it over here. me show you what I've got. It's 42K, and for some reason it doesn't want to load it. That's fine. Yeah, that's fine. I'll just share it directly. So these are the equations here. Can everyone see those equations?
Yeah.
Okay, so these are just what I had written out by hand, and it really just shows us. I wrote it t+1, which means the day in the future. So you can imagine how many are susceptible tomorrow versus how many are susceptible today, and things like that. But let's just let's just throw this in a spreadsheet so that we can see how this actually progresses. So here we are. We have let me annotate this. Our total population size, I've just set this to be 1 million people. This number here, this is the number of people that are infected. The initially infected, so one person bought something from a market in China, and we're all getting the disease he got now. And this is the infected rate. So this is this beta in the equation that I saw before, and this is the recovery rate. So you can imagine the rate at which people are recovering. So in this case, it says 0.68. So what that means is essentially 2/3 of all people that are infected every day recover, okay? And I chose these numbers kind of at random, these two here, at random, because they give me this here, this number. This is that R naught that I was talking about last day. This is the number of secondary infections due to one infection. And this number is roughly what people have calculated the R naught of the coronavirus to be, okay? So I tried to pick numbers that will reflect the current situation. Of course, it's not accurate. It just gives us a way of understanding things. So now let's look. What I did here, I've put this in a chart. So this is the susceptible people, the people that can get the infection. This is the number of infected people. This is the number of recovered people, okay? And these are days, for example. So on the first day, there's one person infected and 999,999 that aren't, okay? And so this guy goes and infects some people, and some people are recovered. And these are, you could think of these as averages. So that's why they don't add up to whole numbers, for whole people. And what I put in there, what you can see if you really are a big fan of Excel, up in the corner here, this is the formulas I put in each of the cells. These are the equations that I derived on the previous slide that had all these complicated betas and gammas in it, okay? So I just put them in here. I put them in there. I put the equations in, the formulas in the top. And I just filled it out. I just kind of selected these guys and I dragged them down and ruined my spreadsheet because I didn't select enough. That's fine. But I just filled down the formula so that you can see how the numbers change over time. And what I did is I've got this chart here that just plots the numbers. And so now what you can see is this looks very, very different than exponential growth. So the infected people, the ones that have the disease, are in the red. So these people have the disease. These red here, they have the disease. The blue ones, these are the susceptible people. So you can see everyone's susceptible, but then there's less and less people that could likely get the disease. Okay, and it goes down like that. And then the people that are recovering, so first people get infected, then slowly people are recovering, and eventually, because I assume it's not a deadly disease, eventually everyone recovers. Okay? Is that clear how you can see that?
Yeah.
So the point here is that we get this little hump. So the disease goes up pretty quickly, but then there's less and less people that can get the disease, so then it slows down. Okay? And then there's less and less people to get the disease, and so then the disease eventually dies out. This is the key thing here. Okay? Let's play with some of the numbers. Let's see what happens if I increase the infection rate. So you can imagine if there were no control measures in place, so people were just free to go to concerts and out to bars, celebrate St. Patrick's Day, like they did at my alma mater, Queen's University in Canada. The students irresponsibly celebrated St. Patrick's Day in a very dense party in downtown Kingston, Ontario, and very, very likely spread the disease around. Okay, so perhaps their infection rate was a little higher. So let's see what happens. When I increase that infection rate, what happens is this whole curve, it shifts. So what it means is that the disease takes off much quicker. And not only does it take off much quicker, it actually goes higher than it does previously. So with the lower numbers, which I can do and keep that, I think I can keep that, yeah. With the lower numbers, look what happens. The curve is much smaller, okay? So if we somehow decrease the number of contacts we have, what we're doing is we're lessening the severity of the disease, okay? It looks like people don't get it as quick. In total, it still should be about the same number of people that get it, but it's spread out over a longer period of time. Now, why this matters is that if we have the sudden spike, like they had in Italy, then all your healthcare resources are overwhelmed. And if you're in a country that doesn't have public health, like in America, for example, then this may overwhelm what resources you have to combat the disease. If you could spread it out, if you can slow the initial spread so that we don't have this spike, perhaps it becomes more manageable. Now let's look what happens if we decrease the rate even lower. I don't know, let's say 1.8 or something. Again, we see a lessening of the severity, the initial severity of the disease. What about 1.6? Again, we're slowing it down, okay? So we don't see that initial severity. So let's just take a little bit. Okay. So not only that, the total number of people that are infected at any given time, here we have 250,000. Up here we had 500,000 people that were infected at that time. So you can imagine if you have limited resources in terms of hospital beds and what have you, which scenario is better? Well, this is what we want to strive for. Okay, questions on that? No questions. Good.